Hi everyone, in this tutorial I'm going to solve unsteady fluid case study. In this case study, water is flowing through a copper duct with inner copper coating as shown in this picture. At first, domain velocity is 0 meter per second and domain temperature is 300 Kelvin, and then water starts to flow. We want to simulate this case study for different conditions. At first part, the water with the velocity of 1 meter per second and temperature of 300 Kelvin flow through the domain, and the wall between the fluid and solid has temperature of 2300 Kelvin. And we want to use the K epsilon turbulent model to simulate the unsteady turbulent flow field. In the second simulation, we have a heat generation. The heat generation starts through the fluid domain. The heat generation is based on the equation given here, and we want to use the UDF to consider this heat generation. And finally, we want to compare the temperature for these cases. Okay. First, we are simulating the case without heat generation. So we need to read the mesh first. So let's check the quality of our mesh. Everything's fine. So we start with general. This is a transient flow, so we need to change the time from steady to transient, and everything else is fine. Pressure based, absolute, and planar. For the model, you need to enable energy. Also, this is a turbulent flow, so for the viscous, you need to change from laminar to K epsilon and use the default value of coefficient. For K epsilon model, use the standard, and for near wall treatment, use the standard wall function. Okay, so we need, for material, our flow is made of water and our solid is made of copper. So we need to copy water and copper from the Fluent database to our simulation. Fluent database, water, liquid, copy. And for the solid, okay, copy. So we have water and copper in our material. We need to change the cell zone condition to this material. So for the fluid domain, we have fluid, and we need to change the material from air to water. Okay, and for the solid domain, we need to change the material from aluminum to copper. Okay, now the cell zone condition is set. We can go to the boundary condition. For the inlet, we're gonna use the velocity inlet. So the water is going inside the domain with the velocity magnitude of 1 meter per second, and we're gonna use the magnitude and normal to boundary. And for the turbulence, we're gonna use the intensity and hydraulic diameter. For intensity, we use 10%, and for hydraulic diameter, we need to calculate the hydraulic diameters, which is equal to 4 area to perimeter. And considering our simulation, our hydraulic diameter will be 0.1818. And for thermal condition, the temperature is equal to 300. Okay. For the outlets, we're using pressure outlet, and also for the turbulence we're using the same as inlets, 10%, and hydraulic diameter of 0.1818, and thermal condition is the same. Surface body is the wall between the fluid domain and solid domain and has a temperature of 2300 Kelvin. So we're going to use the stationary wall and no slip condition for the momentum, and for thermal using temperature of 2300 and material of copper. Also for the shadow, we're going to use the temperature of 2300 and material of copper. For the wall down has a temperature of 300 Kelvin. Also material of copper. Wall left and wall right are both isolated. So you only have to change the material to copper. Wall up is also isolated. So for heat flux, you're using heat flux of 0 and material of copper. Okay, all our boundary condition is set, and we can go to the next step, which is control. For solution control and solution methods, we're going to use the default value, but for monitor and for residual, for continuity x velocity and y velocity, we're going to use the absolute criteria of 10 to the power of -4. And for energy, we're going to use 10 to the power of -7. For initialization, we are using a standard initialization with velocity of 0 and temperature of 300 Kelvin. And for calculation, we're going to use time step size of 1, number of time steps 30, and maximum iteration of 200 per time step, and then calculate. Okay, now calculation is complete. Let's first save our simulation. Write case and data, unsteady UDF, UDF case A. Now we can look at the results. So we are going to surface integral, mass weighted average, temperature, and we're going to choose outlet. So the outlet temperature in case A is 309.9. Now let's simulate the case B and compare the results. So the only thing we have to do is to interpret the user-defined function, or UDF, and then initialize and simulate again. So for that, we're going to user-defined tab, functions, interpreted, and then we're going to choose the UDF file, and then click on interpret. Now the file has been compiled successfully, and we need to assign the heat source to the fluid domain. So we need to go to the cell zone condition, fluid domain, and enable the source term. Then we're gonna enable the energy and choose the UDF energy source. Okay. We also need to change the boundary condition of the wall between fluid and solid. We need to change it to the couple wall. So we're going to boundary condition, part surface body, couple. Okay. You can also see that its shadow has been changed to couple too. So we use the solution method and solution control as previous. We only need to initialize it again. And for calculation, the same settings and calculate. Okay, now we can look at the results. Surface integral, mass weighted average, temperature outlet. The outlet temperature for this case is 308.29, which is about 1 degree less than previous case. This is the end of the tutorial, and I hope you enjoy it. Thank you so much.